event, of course, slowed down enormously. So a collision of the two beams, and what comes out in the detector, and you see the 4 blue lines. This is like a Higgs decaying into 2 Z's, and the HZ goes into 4 muons, for example. Again, such a candidate being produced as we see it on our screens. Okay, so on the 4th of July, we had the official announcement that indeed, in 2012 that was, that indeed we saw a particle in that mass range. And the very interesting thing it was that we saw it in the 2 experiments independently of each other, which is not trivial because the 2 experiments use different technologies, different people, different methods sometimes to search for this excess, and they both saw something at exactly the same place. And that, of course, led to us to believe that we actually found something. And this was announced both at CERN simultaneously and at the big high energy physics conference we just started in Melbourne on the other side of the globe. This is what the evidence looks like in July. And the Higgs is in fact sitting here. This is the spectrum as before. This is the excess, or this is the background subtracted spectrum. So you see the excess here. This is for one experiment. This is for the second experiment. So this is also in the 2 photon channel, both of them. This is in the 4 lepton channel, where you see this peak growing up. And there's another channel, which I will not insist on here, because it has neutrinos in it, it's a bit more tricky, but that was also seen there. So, how significant was this observation? And the way we measure significance is to look at how incompatible the data is with the background only hypothesis. So we make the compatibility plot, which is a likelihood function, and we see if it's compatible with the background, the curve as function of the Higgs mass, whatever we see in the spectra, all the channels combined should give us something which stays above here around 0.5, oscillating a bit around due to statistical fluctuation. However, this is not what the data did. It had a big dip. It had a dip here, and that's for one experiment, and the same in the other experiment had a dip there. And the significance of that dip is measured in standard deviations from being a background only hypothesis. And it deviated just 5 sigma here and a bit over 5 sigma between, around 6 sigma here away from that. 6 standard deviations. To give you an idea, in this kind of technique, if you apply that, it's a matter of what's the chance that you are wrong, that this is still not a signal but just a fluctuation of the background. The chance that you are wrong here is 1 in 3 million. So if you do the experiment 3 million times, one time you will find that. But that's a chance we were willing to take, that we were wrong only 1 in 3 million. Particularly since the other experiment at the same place had the same thing. So the announcement was made, and then this came into the newspapers and stuff. And we had an update. This was middle of 2012. We had an update. And so you see, what you expect with the discovery is that if you add more data, the discovery will grow. And that's exactly what it did. We added a factor of 3 more data. The 5 sigma became now 10 sigma or over 10 sigma. So there's nobody doubting anymore that we actually see something there. And I can show you just how the history works. This will be a fast forward on the next slide from the data accumulated from the beginning till the end, and you'll see the signal grow in there. Look, for example, here. With time, there's a steady grow of the signal, which is exactly what you would expect. I'll play it once again, because this one for the gamma-gamma, one for the ZZ. You see it best on here. As the data grows in, the blue is the expected background, and then that is indeed followed by the data. This is not predicted by the background. This is something new, what is sitting in here. This is a signal. And since then, in fact, we have, as said, we have confirmed it. There are a lot of aspects which we had to verify if this would be really a Higgs particle, namely on how does it couple to the other particles, what is the spin of that particle. We knew it was a boson, it had an integer spin, but we didn't know it was 0, 1, or 2. For it to be a Higgs, it has to be 0, because we're talking about the scalar field, which is the Higgs field, and so the particle associated with it has to be a scalar. We found that it was a scalar. We measured its mass precisely, now it's 125.6, and some other things. So while in the beginning we actually talked about a Higgs-like particle, when we did not have this kind of information yet, after the completion of the run in 2012 and in the first analysis in 2013, we now call it a Higgs particle. There is still a subtlety here. We don't yet call it the Higgs particle, but a Higgs particle. The reason being that some of the couplings we measured only to a precision by 20%. That's all the data which we have accumulated so far allows us to do. And within 20%, this could also still be a Higgs, but not necessarily coming the one which Mr. Higgs has predicted, but rather coming from something related with supersymmetry or other theories behind the standard model, which would show up as deviations from what you would expect from a neural Higgs when we have more precise data. And that is what we will be hunting for when we get the 2015 data and starting to analyze with that. But anyway, on October 8 was a fun day for us. This is again in the same building which I showed before. This is the spokesperson of the Atlas experiment, the spokesperson of the CMS experiment, and yours truly here, celebrating the announcement of the Nobel Prize, which was accorded to Mr. Peter Higgs and Francois Anglaire. In fact, Anglaire worked together with Brout. These were two Belgians. And they at the same time came up with the same idea, so their papers are contemporary, but the particle is called the Higgs particle, so that's why probably Peter Higgs is best known. And this will be definitely what we're going to do next, is study this particle now in detail. We're the only machine in the world that can produce these particles, and many believe that this containing a lot of keys to the next questions, maybe like even to dark matter and so on. Now let's see how I do, but I'm not sure when I started exactly.
10 minutes past.
I started 10 minutes past?
1 hour now.
1 hour, so I should be wrapping up soon, right? That's what you mean. Okay, good. So I'm not going in detail here, but I'm telling you a few other things that we are looking for now. For example, are the quarks elementary particles? And in fact, so far they are. What we are doing, is we're doing kind of a Rutherford type of experiment, like what he did, looking at strange recoils which we may be getting. And we look at that, and we looked at through jets, and we find so far, and just this is the only plot to remember, that this is the data, this is if there is nothing special happening, and this is if there would be elementary, smaller constituents, preons, sitting into the proton, which in the quarks, which we don't see. So at the moment we think up to the level of 5 times 10 to the minus 18 centimeter, these particles are still elementary. Are there extra dimensions or mini black holes? I will probably only mention the last thing. So the extra dimensions come actually from the question that the electroweak scale and the scale of gravity seem to be very, very different by something like 17 orders of magnitude. And that makes many people uncomfortable, and they think maybe there's something in between there, and maybe there's something happening at some stage that in fact this scale is just a mirage, but that is what really is happening as soon as you break open extra dimensions, which could be phases or so for the points in space. And we haven't found them yet while we are looking, and so far up to 9 TeV or so there are no extra dimensions. But the upshot is, if there were extra dimensions, then, and this is what some people were afraid of, we could make these so-called micro black holes. These are micro black holes, but we know if they are from Hawking and others that they would be quite safe, in fact, because they I think I'm running out of batteries. that they would decay even faster than a Higgs particle, to 10 to the minus 27 seconds, so they would be quite safe. In any case, we have not found them yet, although we found some nice events which could look like that, but they could be just background. But we have, of course, a strong interest from some people watching us if we find something like micro black holes. This is when Steve was visiting us a couple of years back, because that could be ultimate proof for his theory if we actually would see these objects to appear. All right, I'll probably skip this and just show you that we also do heavy ion collisions to create a primordial plasma here. And this is one typical event. It's again a movie like before, a real event. And you see the collision, but now you see a whole lot of particles coming out. If you hit two nuclei together, you get a whole sort of debris in the detector here. So to summarize on that, what can we say? We have this discovery of the Higgs. The elementary particles, so far the quarks are still elementary. We haven't seen substructure. We haven't seen supersymmetry, I skipped that. But we haven't seen any extra dimensions, and definitely we haven't seen any black holes yet, so you should be afraid of that. So what we study, and that's why I call it the Big Bang machine, we study actually with the Higgs. We're going to study this 10 to the minus 10 seconds after the Big Bang. This is where this electroweak phase transition, or the fact that the Z's got mass and the photons remain massless, is actually the place where we're discussing that. And with these heavy ion collisions, it's 10 to the minus 5 seconds, so much closer to us, in 5 orders of magnitude on logarithmic scale, we study these phase transitions. So that is what we study, basically, by trying to recreate particles such as the Higgs we have here, to study the first 10 to the minus 10 to 10 to the minus 5 seconds in the universe. So, as promised, a few comments that CERN, which looks like a big machine, and it's in fact one of the most complex instruments we ever built. It's a very complex machine we have. But there's a lot of spin-off coming from CERN, from the technologies, for example. So CERN is also a lot with technology transfer. I mentioned the grid computing, and I'll give some examples just on the last slide, which I will have there. But the detectors we built are based typically on very advanced techniques of using silicon detectors, microchips, and so forth. They are now being used, some of the detector components which were designed for the LHC, are now used in the medical area for making pictures with high efficiencies. The Medipics, medical X-ray diagnosis, for example. We also have areas where we produce radioisotopes, which are for medical applications, and see just radiography of a bat, for example, which is done with instruments made by CERN technology. So for the grid, the computing, it's very essential for us, because we have this huge amount of data which we must be able to crunch and deal with. But now domains like archaeology, astronomy, civil protection, computer chemistry, earth sciences, financial simulation, well, maybe they're not all so good. Fusion, geophysics, energy physics, life sciences, they all have bought into that. They are all now following this model and use to a large extent the software and tools developed by CERN for their own needs, but now in these communities. And I think it will, like the World Wide Web, which was also invented by CERN, it will get a very big acceptance around. And at CERN itself, we have many programs that work, like accelerator school, fellowships, doctoral students, physics schools, computing schools, technical students we take, teacher programs, even which some countries come with us, outreach programs, of course our visits. There's a lot to do and a lot to, you can benefit from, particularly the summer student program, I strongly advise. Okay, finalizing, aerial view of CERN. The main message, what I want to give is that we have, since summer 2012, in the CMS and Atlas experiment, found a new particle, which looked at the time very much like the long-sought fundamental scalar boson, as postulated in '64 by the people who got the Nobel recently. In March 3/4 of a year later, we used the full statistics, and then we confirmed the existence, and we measured properties which actually confirm that we are dealing with the Higgs particle here. This is a brand new particle, I should say. We never ever saw a scalar particle, a fundamental scalar particle in nature. This is the first time we see it, and I'm sure it is still surprises for us when we are going to measure it in detail, things we didn't anticipate yet. The Higgs boson itself is a bit of a mystery now. It's light. It's like 125 GeV. It's 125 times the proton mass, but it's still light. So that itself opens new questions, like what is going on? Questions we were addressing already, but now even with more vigor and intensity, because we know something has to stabilize that mass of the Higgs to make it not run off to become infinite, for example, as the Higgs would like, because it likes to couple to mass. And this is what we're going to tackle in these next few years we have. So to end, we are on the verge of a revolution in our understanding of the universe, I think, and our place in it. Egyptian scientists participate. Interested students or seniors can join this through the NHAB, which I mentioned before, because I believe this program is just starting, and we are really just at the beginning, and there's still a lot to be discovered there. Okay, thank you.
We can open for questions. So, if anybody has questions. Okay.
Is the standard model sufficient to explain all the data? Or?
No. The standard model is explained for whatever we do at the colliders, for example, and whatever we do at our scales of fundamental physics. But the one big mystery of the standard model, I have to skip it due to time at the end, is we know there is something like dark matter. We know that there is, in the universe, I may quickly go back to it, there is more probably than the particles which were in my table. The table which I had, which was the like the Mendeleev table, the table of the components. I went too far, I think. And we know that from observations, and that's what I want to get at here. Next, yeah. We know that from observations of rotations of galactic clusters, the outer sides they seem to move too fast with respect to the calculation you would do based on the matter, based on what you see from the luminous matter. And it's a big factor which is missing. In fact, it's a factor 5 of mass missing, which is dark. We don't know what it is. We don't think it's any of the particles we have in our thing, because we should have seen other signatures of that. So it's most likely a new kind of particle which only interacts with us gravitationally. So it's very, very difficult to find it. But we think we may have some ways of producing it.
Okay, Dr. Radi?
You mentioned that in 2015, the LC will start using energy 13 on 14. Why?
Oh, so the question is, for those who didn't hear it in the back, I said the end energy or the maximum energy of the LHC is 14 TeV, but I mentioned that if we start in 2015, we will start only at 13 TeV. That is correct. It's not necessarily so that the whole year we will be only at 13. We may go up later in the year. But the main reason why they want to go to 13 TeV is the following, that is a feature of superconducting magnets. So all the superconducting magnets were trained on surface when they were constructed to have to reach the field so that we can go to 14 TeV, because the higher in energy we go, the higher the field in these magnets is. They are the delimiter, in fact, of the energy we can reach. What happens with superconducting magnets, and that's a feature known to experts, we have to, of course, to transport them in the tunnel and install them. So we have to transport them over kilometers and put them in the tunnel, connect them up, and so on. And then you start them again, and then they don't reach that high field anymore for which they are constructed, but they quench before. And so within the last 10% of reach of the field, magnets can quench. And this is not a problem, but it's time delay, because then the magnet goes off, you have to start again, and so forth. And so we think we need something like a few thousand artificial quenches all around the ring to have the magnets trained so they can go to 14 TeV. While for 13 TeV, it's maybe a few tens to 100 quenches or so we have to do. So that's the reason why they say we start with 13 TeV, because we probably don't have time to quench all the magnets, to do the artificial quenches, so that they're all trained to be able to go to 14 TeV. It's a matter of time until we do that.
Okay, another question? Yes.
My name is Mohammed Izzat. I'm a student of physics, third level. I wanted to ask. I want to ask about something in the example of Professor David Miller.
Yeah.
About the mechanism of Higgs field.
Mm-hmm.
If when the famous person entered this room with two doors, okay?
Yeah.
When he enters, he has some specific properties.
Yes.
Which make all peoples, these peoples want to take attention. Okay.
Yes.
So what is other specific properties of the elementary particles like quarks or leptons to make this Higgs field interact with it? Is a charge, mass, but this field give it the mass.
Mm-hmm.
I want to understand this thing. What is the specific properties which make these elementary particles interact with the Higgs field?
Excellent question. You should actually come and work with us, because we have the same question right now. We have the same question. What we have explained so far is how it works. But we have not explained why Einstein gets as heavy as he gets heavy, or what is different for the particles, why are some particles Einsteins and some particles are, young students or something like that, which go to the room. This we don't know yet. And that is what we hope to actually unveil and discover still, that the exact value, why the electron has a particular mass 2,000 times smaller than the proton mass, or the top quark has a mass 200 times heavier than the proton mass. There's a big difference. And we don't know from looking at this particle why would this be the case. So this is our next step, trying to understand. We know now how it works, but we don't know why they get these numbers. That is still a mystery.
So, another question. So till now, I can understand. Till now, we can describe what we care, but we can't answer what. Okay.
Mm-hmm.
Another question about the graviton. I am permanent survive on the website of CERN, and I saw I have watched the video about for students in school, and I see five forces in the nature. CERN added a new one in which called the Higgs field.
Mm-hmm.
Okay. But they mentioned a graviton, which
Mm-hmm.
make gravity. Is there a plan in CERN to search or find a graviton in the future or not?
Yes. The way gravitons could be seen at CERN is through these extra dimensions. I can go back to that. In fact, the way we could see eventually extra dimensions, if extra dimensions would exist and gravity would get strong, we would couple much more strongly to gravitons, and we would actually start emitting gravitons. And as you see here on this picture, we would look for events which look of this sort, where we have a parton coming out, a jet of particles coming out, and a graviton coming on the other side. So if extra dimensions exist, then CERN has a chance to see gravitons being produced in the experiment. Now a graviton will not interact with the experiment, it will be only weakly interacting, but it will be something very missing, very unbalanced in the event. That could be the signature of the graviton. These are one of the possibilities. Another possibility is if a graviton, like you see in the smaller diagram, would make a resonance on top of things. But you see that this is what you would expect, this is the data, no resonance so far. So if that exists, we can say something on gravitons. There are other experiments in the world which look for gravitational waves, for example, which may come from supernovas or so, and they would also see the effect which you could relate to a graviton. But that's the way we address them experimentally.
Can I ask another question? Or?
Yes.
It's up to the chair, so for me I'm okay.
Yeah, okay, yeah.
What about the fundamental particles, quarks and leptons? They made the matter, or the matter consists of quarks and leptons. Only quarks and electrons. Okay. What about other muons, kaons, and so on? This exist in the universe, but don't enter the constitutive matter, or what?
Yeah. So I think you've been doing some homework here, so that's good. So I can give some. I can go back to my table. I would appreciate if you would have had the question so that I don't have to zap like crazy. But
Then he will
okay.
answer.
All right. So as I said, for matter as we have it, only the first two quarks are needed, the U and the D quark. They make up neutrons and protons. Yeah. And only the electron, because you can have the electron which makes the atom. That is how they're made in the world. In fact, you can make atoms also with the muon. But the muon, due to its mass, and that's been done actually, due to its mass, will be sitting much closer orbit to the nucleus, and then we would be much more smaller than we are now by a factor of 200 or so. Moreover, the muon is not a stable particle. The muon decays after microseconds. So these atoms are not stable. So the only stable ones we have here are the E, U, and D, which are stable. All the others are not stable, and they decay to the lightest components. So therefore they don't make up matter, or you don't see any matter that is made up. By the way, there is some scare that if the S quark here would enter matter, it could eat up these quarks and make everything S, by the way, and that's called strangelet matter. There are some science fiction novels written on that. We haven't seen that in reality, so not to worry. But now you can ask the question, why do we need the other guys if they don't make up matter? And in fact, it turns out they are very essential. And they are very essential for a very subtle point. But the point that makes us being here. That's namely the difference between matter and antimatter creation. And a phenomenon that is called technically, but since you read a bit about it, you will understand me, technically CP variation. That's charge and parity invariance. And what it means is that you may have a particle and you may have an antiparticle. They are composite. For example, a meson with a B quark in it and an anti-meson with an anti-B quark in it. They will decay to other particles, to the lighter ones, the final ones, but in a slightly different way. And for example, here you get 3 pions, and here you get 3 antipions out. And therefore, the thing will not add up if you have matter and antimatter produced. At the end, after all the decays, you will have a little matter left compared to the antimatter, because the matter and the antimatter particle decayed differently. And in order for something like that to work, you need at least 3 generations. They're called generations, these 3 blocks. So UD is 1, CS is 2, and TB is the 3rd one. You need at least 3 generations in nature. And that helps to explain that we could be living in a matter world. We haven't found the CP violating reaction yet. We think it probably was in some new physics particle, not in the particles we know today, but the principle would be that one.
The last question, please. About in the medical application of CERN, of the Large Hadron Collider, I read a paper before about the treatment of the cancer. When we hit antiproton to the proton of the cancer, okay, we can damage it. It's work or just now it's work or just
no. We actually have already some of these cancer therapy accelerators in place on the world, and they are starting up now with real patients. So it is not science fiction; it's for real.
Yeah, thanks.
Another question, okay?
Professor Amer from Mathematics Department. Thank you very much for your nice talk. In fact, I am a mathematician, but I have really enjoyed by your talk. I have only one question about the equation E cap equal mc squared. In fact, you are using your standard model and your calculation already have considered this equation. Since sometimes I heard that this equation already changed it to E equal 1 over 22 mc squared. I don't know if this is really, true or false. And if you changed your equation in your standard model, if this will give new things, or I don't know what will happen in your model.
Okay, so actually it's funny, I gave the talk, a similar talk 3 days ago in Bahrain, of all places, and also I got a question on E is equal mc squared, so this must be a region where one is really worried about that equation. So in fact, it doesn't enter the standard model as we use it as such. It enters the special relativity. There it enters, and through that it can be used. But for our particles and for our interactions, if there is a deviation from that, we wouldn't actually see that at this point. Now I know to a good extent that at the energies we are working there's no deviation, because if there would be, the accelerators wouldn't work. For the simple reason that if we bring up the energy of the beam, the mass of these particles increases, and one has to synchronize the whole machine carefully and accordingly, which is a very tedious job, and this beam is circling 11,000 times around in the accelerator per second, and we keep the beam like for 10 hours. So within that precision, E equal mc squared is fine. And for anything else, I think for the production itself, for the Higgs, it doesn't have from test. It doesn't mean that E is mc squared is ultimately completely correct, but we are not testing that really.
Another question? Okay.
Ibrahim Adel, I'm a student, but don't worry, I will not ask you many questions like that.
No 5 or 6 questions, okay.
Only one question.
Okay.
We, as a student, we are really excited to solve many mystery puzzles in the universe. What the next plane in the future in this moment?
Sure. So for us, first of all, we go to the energy, we bring it up by a factor of 2 or so. That doesn't seem much, but it's actually a lot. And that will may mean the difference between seeing and not seeing new particles, which we all expect to sit close by, now that we know what the Higgs has done and where the Higgs is and how the Higgs works. We believe we must have something very close by, because otherwise it's very difficult to explain why the Higgs mass is exactly at that value. So this is what we're going to do next. Now it may be difficult to see that. It may be either something that jumps to the eye, and then in 2016 there will be somebody here, me or somebody else, giving a new talk saying, and now we discovered this fantastic supersymmetric thing, and we know now we're all supersymmetric and so forth. That may happen. May also happen, it's much more difficult, that it's much more subtle, and therefore we need a lot of data. So the machine, or CERN has a plan, at least for the next 20 years with this machine, for constantly upgrading it. Probably not so much in energy, although it may be possible still to go a bit up in energy, but particularly in the event rate, so in the collision rate. So looking for more and more rare and subtle things, like by a factor of 100, they think of increasing the collision rate. That's one thing. The other things is that if we now have this Higgs, we know what the LHC will be able to do, but there will be also some limitations because of the nature of the collision. Hadrons colliding, which protons colliding, they are bags of quarks and gluons, so it's a bit dirty. It's cleaner to do electrons. They are point-like particles. They are elementary as far as we know. You can control much better your collision if you do E plus E minus. If only we could have them at high energy. We couldn't, so we built this machine. But now we know how to build a machine which is not quite as high in energy as this one yet, but high enough, for example, to become a Higgs factory. And by studying the Higgs, by knowing the properties up to the percent, we believe that the Higgs is, the coupling is going to tell us something of what we call the dark sector. Dark matter, dark energy, through coupling through that. So even very precise measurements of the Higgs is going to be very important. So these are the immediate ideas which are going around for this. There are also now new ideas starting around of a new collider which is 10 times more higher in energy than this one. It will be 100 kilometers in circumference, and apart from CERN, surprisingly, or maybe not, the Chinese are actually bidding for that. They would like to have such a machine of excellence in their country. That is what I can see for this field.
Okay, last question. Okay.
Can we consider particle a dark matter, or dark matter is a new type of matter doesn't exist on the Earth?
So, okay, I'll go to the mic. So the question is dark matter? Is dark matter a possible new kind of particle, or is it something that doesn't exist on Earth? In fact, this room should be full of dark matter. Any room or any place should be full of dark matter. Just dark matter ignores us completely, but it should be there. It's not something which is only in outer space. It's also here. It's going probably through you right now, if it exists. That's why it's possible to build experiments underground here which look for collisions of dark matter particles with some atoms on a crystal, and see if there is actually a reaction and some heat generated or a signal generated, to look for this kind of things. Now, dark matter itself, we actually do not know 100% for sure that it is a particle. There are also other ideas in trying to explain dark matter in things. Sometimes even trying to change, maybe it is a change of the Newton laws which we have to change, and there is no effective matter. But the biggest money, I would say, for theorists and the community is on dark matter. Should be a particle, very weakly interacting, probably only gravitationally or maybe very, very weak. And it should be, if you look at the freeze out of the universe, and if you look at how much dark matter we see in the galaxies, it should be a particle with a mass of round about 100 times the proton mass, like the Higgs. The Higgs can't be dark matter particle because it decays, but it should be a stable particle. But something of that mass should be the case. And I got here a message that for those who are listening to it, this is just an advertisement spot for a moment, that I'm giving actually a course on Tuesday and Thursday on particle physics at, I think the one is at Shams University on Thursday, and then on Thursday in BOE. So for those who are interested to hear more and have more questions, you can always come there. End of the advertisement.
Okay, we would like to thank Professor